to introduce today's CaJAGWR seminar speaker, Dan Kasen. Comes to us all the way from Berkeley. He got his bachelor's at Stanford and did a prize postdoc at and then he came back west for Hubble Fellow postdoc at UC Santa Cruz, and then returned to Berkeley as faculty. And he is going to tell us about all the interesting things we learn from energy astrophysics that's not directly from gravitational waves.
Great. Yes, thank you. Thanks for having me out here. I really enjoyed visit and get to see all the great work that's going on here at Caltech, especially in this field. This is not a new topic, I'm sure, to many of you in compact object mergers. And I'll talk maybe hopefully something a little different, which is the electromagnetic counterparts, in particular these radioactive counterparts, the Kilonovae. Hypothetical sort of events, so to speak. We don't have much data on these, they're sort of theoretical idea. But I think I'll try to impress upon you that in the last several years, the theoretical picture of them has gotten a lot richer and allowed us to tie what you might see from these sort of events to a lot of interesting physics in the compact object merger. And hopefully, in the next few years, we'll have a lot of great data on gravitational wave sources and Kilonovae and all that. And it'll be a very exciting time. Let me just point out a few people working on this who've done a lot of the work that I'm talking about. Rodrigo Fernandez, a postdoc at Berkeley, Jennifer Barnes, who graduates from Sherwood's done some really excellent work as well on aspects of this Kilonovae. So, we can't even really see this image, this movie, but I guess you can imagine it. Just to set the stage, I know you guys have seen simulations of neutron star mergers before. This is one example of it. Where I could just claim this is a black hole. It's not expect to see anything. So there's two neutron stars there. This is one of the simulations that's on Roswell. I think it will come up a little bit more. Just to set the stage, there's a lot of groups all over the world working on this, including a lot of people doing great work here. This is just one example of what happens when you have two neutron stars coming together. Wave emission and merging, and I'll just point out some of the features that will come up throughout the talk. So it's a lot better now. So here's the neutron stars merging together. They get distorted and merge together. You see a little bit of material getting flung out, not a lot, maybe 1% or so. That's how much is flung out. Most of the mass going into this central remnant, which may survive for some period of time as a hypermassive neutron star, but then likely collapses to a black hole at some point. How long it survives will depend upon some things that we don't know, what the maximum mass of a neutron star would be, which will depend upon the equation state of nuclear matter. Also, if there's some additional support through differential rotation, perhaps thermal support, all that can survive. But maybe there's some period of time that survives before collapsing to a black hole. And then the last thing to notice is that some material, maybe a tenth of the material most, gets hung up in a disk around the remnant and will gradually drain on. And this will all set the stage for what we might see electromagnetic within these events. So while studying these things, I don't really have to spend too much time on this, because I think you know that the accretion of material, say, onto a black hole may power short gamma ray bursts. So these are our leading progenitor short gamma ray bursts, although we lack some real direct evidence of that. There's a lot of circumstantial evidence. One thing I like to talk about a lot is that these mergers may be the site of heavy element production through the R process, which is rapid neutron capture, which is one of the biggest open questions still in nuclear astrophysics. Where are these heavy R process elements made? The other candidate site is usually core collapse supernova, but simulations have had a really hard time getting core collapse supernova to produce a robust R process. So the neutron star merger has become a more appropriate candidate for that. Whether the neutron star mergers can produce all the R process elements in the universe will depend upon a couple of things we don't know. One is how common they are. In the rates of neutron star mergers to neutron star black hole mergers are pretty uncertain right now, but that's hopefully something LIGO will tell us in the future. And the second thing we don't know is how much material may actually get produced in each neutron star merger event. And that's something I'll argue maybe we can figure out through following electromagnetic counterparts. So this may be a question we'll be able to address at some point in the future. And then, of course, these things can produce gravitational waves, which is like we'll see soon. And a lot of astronomers want to follow up to find electromagnetic counterparts, which will be able to enrich the science in a lot of ways that I'll try to discuss. Maybe various electromagnetic counterparts, two in particular that stand out. One is, of course, accretion on to the central object, and they produce a relativistic CaJAGWR burst. And we see these things, and they're incredibly bright, so the next counterparts in that way. But of course, the emission is highly beamed in this relativistic jet. So you have to be very fortunate to be looking, sort of down the jet to be able to see this emission. And so it's unlikely that any light source would have that sort of limitation. So I'll spend most of the time on these kilonovae, which are the material that get flung out at non-relativistic speeds during the merger, or subsequent to the merger. Some cloud of debris that's probably heavy radioactive stuff, and will power a radioactive glow, sort of like a dim supernova. This is not a kilonova, this is just some image of a supernova remnant that I picked off of Google, but it's probably something kind of what you expect to see from a kilonova. Some quasi-spherical cloud of radioactive debris. And since it's non-relativistic, the emission will be isotropic, so you don't have to have a fortunate moon to see it. So a lot of effort will go into trying to find these counterparts to gravitational wave sources. Of course, the challenges are to know what to look for and how to find them. And you've probably seen that, initially LIGO will not have very good localization of its sources. They'll have error boxes that'll be some 100 square degree or more range. And so that's a lot of area for astronomers to try to cover and try to find these dim kilonova events. Maybe more significantly is the universe is a pretty active place. So if you look at some big swath of sky like that, there's probably a lot of transient things happening, whether supernova or weird stellar explosions and such. And so actually picking out the kilonova from all that other confusion will be a challenge, and something theory can hopefully provide some guidance on what signatures to use to try to select the actual counterpart to the gravitational wave source. I'll argue that color of the kilonova would be one of the main diagnostics, of course. So that's what I'll really talk about. What are the color of kilonova and what do they tell us about the physics of compact object merger? I thought for fun I would phrase it as sort of an epic battle between good and evil. I guess this is from the observer's point of view. The observers would like kilonova to have a nice blue optical color, and that was sort of initially what people thought. Because, of course, it's easy to observe in the optical. We have big telescopes and sensitive detectors. And I'll say kind of briefly that some subsequent modifications suggested that most of the emission we may see will be infrared, which is unfortunate in the sense that it's much harder to observe things in the infrared. But actually it's fortunate in the sense that it's pretty distinctive characteristic of these events that maybe will allow us to distinguish them from other sorts of information. And it's been most challenged, recent work that suggests that the real event may be a more complicated superposition of both these things. So we may have both blue and red emission from this kilonova, and the relative amount of it may tell us something about the details of the physics that's going on in these mergers. So let me just kind of review the basic picture for you before we get to some new stuff. So the idea I said, material gets dynamically, or it gets ejected from these merger events. There's a couple ways that can happen. First, as the merger happens itself, you can have material just basically flung out dynamically on the time scale of the merger, so milliseconds. If you had a large mass ratio, say a massive black hole with a neutron star, this is simulation by Francois Foucault at Berkeley, you tend to tightly distort the neutron star and fling out material in the tidal tail. If you had a more equal mass merger, say between two neutron stars, they almost kind of fall on each other and collide, and the material kind of squeezed out from this interface. Slightly different conditions, it'll be shot But either way, you tend to eject somewhere on the order of 10 to the minus 4, 10 to the minus 2 solar mass material. The actual amount depends upon things, for example, the mass ratio of these stars. Also things we don't know as well, which you see, the matter which sets the radius of the neutron star. So the neutron stars are such that the radii tend to be smaller. You can imagine this collision between the two things tends to be a little bit more dramatic, and you tend to eject a little bit more matter. Okay? And discuss the moving and expansion velocities of a few tenths of the speed of light, basically escape speed from the surface of a neutron star. The thing that's gotten a lot more attention in the last year or two is that there may be a comparable amount, maybe even more mass that's ejected after the merger itself on longer time scales. And that's due to material that, as I said, is hung up in a disk around the central object and will accrete onto the central object on longer time scales of seconds, basically the viscous time scale, the time it takes viscosity to allow transport of angular momentum to and actually the viscous heating that's going on in this shearing disk can heat up the disk and underlying material and blow off wings. You may blow off a significant amount of material in the wings. There can be other processes that help blow off material in the winds, nuclear processes, recombination of particles to alpha particles can dump in some energy and blow apart part of the disk. There's neutrinos being radiated from the hot inner regions of part of the disk that can drive a neutrino-driven wind, although these in fact seem to be subdominant compared to just the viscous heat. So a good amount of material may be flung off after the merger, timescales of seconds of these winds. The conditions will be quite different and may actually lead to quite a different sort of kilonova signature. Expansion velocities will be quite a bit lower too, because you're talking about the escape velocity for this more extended disk rather than for the surface of the neutron star itself. Yeah.
Because this field, this is a little new for me. I always struggle with the word wind in this context. So, is wind here, you mentioned heating, so when we say wind, should I imagine photons that are coming out because things are getting hot, like thermal photons, or what is that? What does the word wind mean in this context?
There's not really photons, but it's just it's a word to describe basically it's mass outflow from the surface of the surface of the disk. So you have material viscously getting heated there. Some material near the surface may become hot enough to be held down and just wait for them to go off. Or photons can't go anywhere here in this distance, so often the neutrinos can escape out, and so they can drive the neutrino-driven wind, kind of analogous to photon-driven wind in the star. So there's those processes. It's just mass getting blown. Some of the masses are creeping into the black hole, some is getting blown off at the same time. So yeah, what is the stuff that gets blown out? Initially, the material of the disk is maybe just some collection of nucleons, protons, and neutrons. Since it's neutron star material, it's going to be more neutrons than protons. And because we use this YE parameter to describe sort of how neutron-rich the material is. Electron fraction is really the same as the proton fraction. It's 3 protons. Now we see neutrons plus protons. And since this is a neutron-rich material, this number is going to be less than a half. And it may range in what we'll see in the outflows from the neutron star itself may be quite low, 5 or less. Material in the disk may be raised to higher levels. And of course, so basically you have some mixture of protons and neutrons, and in this cartoonish picture what happens is we grab a piece of neutron star and throw it out into space and decompress this material, and these nucleons can start combining to heavier and heavier particles. But gradually through some process, the alpha process will build up into heavier seeds. So these may be seeds around the iron group or a little heavier than iron. And then you'll also have around some free neutrons, since you have an excess neutrons to start. Some alpha particles as well. So you build up these seeds. These can't really get too big because of the Coulomb repulsion between them. So if you want to make even bigger nuclei, you start throwing neutrons at them, building it up one particle at a time, and that neutron gets down to a proton. So you sneak the nucleon in as a neutral neutron and produce big. So this is kind of a cartoonish picture of the R process. rapid because you're having many more neutron captures. Before you can beta decay. Okay. And so that's sort of the end product of the outflows from the neutron star merger will be sort of heavy seeds that process heavy nuclei. This is a more sophisticated picture of what's going on. This is by Jonas here at Caltech, and Luke Roberts, who built this really nice nuclear reaction code to actually calculate the nuclear reactions that go on. And this is just one example of starting out with some material that's a relatively low YE, showing what sort of nuclei exist. And so this is a chart of nuclei. This is the number of protons here, and the neutrons here. These are the range of nuclei you can have, and then these boxes are stable nuclei that are not radioactive. And for this initial condition, you start out with some seeds that are a little heavier than iron, and then there's some neutrons and other stuff as well, so the color-coded nuclei is telling you the abundances, and then if you let this thing sort of expand and decompress, you'll see that process that I just talked about happen in reality. You'll see the neutron captures and beta decays driving this composition flow all the way up the chart of nuclei. It's the heaviest sort of nuclei you can imagine. And that happens rapidly on a period of a second. You sort of build up there. And then after a second or so, the neutron capture freezes out, and things just start to beta decay back down to stability. On a much longer time scale, on time scales of hours or days or weeks, all this sort of radioactive waste is kind of what it is. It's basically decaying back down to stability. And notice one thing in particular here, which is important for what comes up, is that as this flow goes up the chart, it kind of gets hung up with these lines here. These are, of course, the magic nuclei, the Kilonovae nuclei that are particularly stable to beta decay, and so it's sort of a bottleneck where nuclei tend to build up here and giving you sort of two peaks in your abundance distribution. Okay. Oops.
And that ability, so that R process, you said something like it depends on the expansion. So is it strongly dependent on the density of the material? What's the physics of the
Depends. Yeah. So it depends on the initial YE. So the more neutron rich, the kind of further heavier nuclei can build up. It also depends upon the expansion time scale, how quickly it's expanding, and also the entropy of the material, in a sense. How many seeds you make per, how many neutrons you have per seed. So people study this a lot, in sort of certain ranges of this. You get different sort of abundance patterns. For very low YE of, say, 1 or something, you almost always have enough neutrons to build yourself all the way up to sort of the heaviest nuclei. Yeah.
The peaks in the stable distribution were at slightly lower atomic weights than the magic numbers. Are the positions of those final peaks at all sensitive to the balance of different time scales? Like does exactly where it is relative to the magic number depend on how much what the lifetime of this is?
Right. Well, so what happens is you'll see so stuff rides up here on this neutron-rich side. You get more neutrons and protons on this side. Yeah, it gets hung up here at these magic numbers. Then it starts to beta decay. So beta decay moves you this way in the plot, right? You turn the neutron into a proton. So that's what you see as it moves, as it beta decays from one point. So yeah, where you wind up in your peak kind of depends upon where you ride on this spot. If you ride up very, very neutron-rich because you have a lot of neutrons, you'll end up here, you'll decay on here. If you have less neutrons, your path will go sort of closer to this stability. When you beta decay, you won't. So yeah, the peak is somewhat sensitive to the conditions, but it's all highly into the percent.
Yeah, that's
Okay. Okay. Yeah. So here's kind of what the abundance distribution is by another group looks like for one of these very low YE. I think it's 0.1 ejecta, showing the abundance distribution as a function of the atomic mass. And you see it agrees really quite well with the solar abundance of our process elements for these heavier elements. And then kind of deviates here. So you kind of make a distinction sometimes between what they call weak arc process and strong arc process. It's a very low IE ejecta is to make mostly the strong arc process. And I'll show you in other parts of the neutron star merger, particularly winds, you may fill up this region of lower mass elements as well. Processes. But you see here the two peaks associated with that, those magic numbers. So that's what we get. Here's another cartoon picture. You know, we inject this heavy elements from the neutron star. It's initially very opaque, so you can't really see anything from it, even though it's radioactive. So you have to wait for this cloud to expand to some large radius and become translucent. And so it's expanding at speeds, 10 C. So after a day, it's actually reached a radius of about 10 to 15 centimeters. So you're taking something, the size of tens of kilometers or something. After a day, it's about the size of the solar system. Densities have dropped from something that was maybe close to nuclear density to something that's 10 to minus 13 grams per centimeter, 10 to minus 13 times less than water. So it's a very dilute plasma now. And the conditions when we're talking about the Kilonovae are really quite different than the conditions you have in the neutron star merger itself. And so that ejecta is cooled a lot during that expansion, but it's reheated by all this radioactivity that continues from these heavy elements. You have beta decay of heavy elements producing these products. You have fission, indicated delayed fission. You may even have some free neutrons that are left over after the process, and those will decay later at a short time scale, 15 minutes or so. So all these things are heating up the ejecta, maybe heated out to temperatures not that different than the sun, 5,000 Kelvin or so. And that will be the emission we'll see to some degree radioactive wall. And so the model, what you see from Kilonovae is basically a problem in radiative transfer. You have to first know the composition and the radioactive heating rate that's going on, and then you have to see how these radioactive products get thermalized in the ejecta and heated, and then you have to follow the transport of photons as they sort of diffuse their way through this optically thick cloud of material, and then you create the light curve. And so this is just showing you radioactive heating rates for various different materials. They kind of just fall off for power a long time. And just to emphasize that the heating from radioactivity is not from one species, it's from a mixture of a lot of these different nuclei that fill the whole chart of nuclides that we saw below. And they're all beta decaying or fission and so on. So here's kind of just a sample calculation of what one of these kilonovae would look like. The simplest assumptions, this is a model done of the kilonova light curve, compared it to a type 1a supernova just for reference, and you can see it's 100 times dimmer and a few days long. This is just a fact of the low masses involved. There's 100 times less mass in these kilonova than type 1a supernova. Brightness kind of just goes with the amount of radioactivity you have, so the mass is decayed. And the duration is really related to a diffusion time through this optically thick cloud. And so it depends on the mass, but also the opacity, which is the big, one of the big uncertainties. Originally in this calculation, we assumed that the opacity was kind of similar to what we think in most astrophysical mixtures, sort of iron-like dominated opacity, but given that this material that we're injecting here is quite a bit different, the opacity turns out to be quite a bit different. And here's sort of a sample spectrum of what you would like, what you expect from one of these kilonova for iron-like opacities. It's, it's like I said, some sort of blue-greenish transients with 6,000 black body. There's some broad features here, very broad because the velocities of this ejecta is high, 3/10 of the speed of light, so all features get sort of broadened out into resolutions. So that was the idea. The main uncertainty there, of course, is the opacity of this material. It's quite weird stuff. So the next approach, the next insight was to look at really what the opacity of these heavy elements were and how that may affect what we see in the kilonova light curve. And if you want to think about what opacity is like in one of these kilonova debris media, you have to think about what's happening to photons as they move through this debris cloud. They are, this whole cloud is expanding, so the wavelength of the photon is constantly being Doppler shifted relative to the local comoving frame. And it's kind of like the Hubble expansion of the universe, so the photons are always Doppler shifting to the red as they move through. So a photon comes along, and it comes here, and it feels the opacity of the state. And so the resonance with one line scatters around, gets passive, and kind of move along, hit another line, scatter around, and so on. So the mean free path of photons in this sort of expanding medium is really set by the density of these lines, or the density of the force of lines. It doesn't really matter how strong these lines are, it really matters how closely packed they are, how far the photon can go before it hits another. And so what you like to do to know the opacities is you have to know all the different line transitions that you'd expect to be present in this mixture of odd heavy elements. And the problem there is we don't have a lot of data for these high disease species. And it didn't exist, and we've done some work doing atomic structure model calculations to try to predict what those atomic structure and lines would be. So it's basically just doing a many-body quantum mechanics problem, looking at what all the energy levels and line transitions are for some of these species that we don't have much data on. And we've done it for a few species, not all of them. You get a certain amount of lines, 40 million or hundreds of millions of lines for these species. So the situation looks kind of complex. There's uncertainties in these atomic structure models, which means we can't really predict the wavelength of any one line with great accuracy. But since there's so many lines, a lot of those uncertainties sort of wash out, and we get a basic picture of what's going on.
What are those, what are other sorts of uncertainty? I assume quantum mechanics doesn't, I assume that works. So what are the uncertainties when you go to calculate a complex algebra?
It's just you have to do it with some approximation when trying to solve this problem. So then there's sort of scaling parameters that come in that sort of mess up it. You kind of modify your wave functions to try to. Okay, what's typically done is people take they take these scaling parameters and they tune them until they match some experimental data they have. So maybe they've measured a few energy levels in ground state and they tune their scaling parameters that are free until they fit those experimental data, and then they say, okay, I've calibrated my model, and now I trust that all the other levels and lines are well treated. And so that's a tedious project, and we haven't actually done all that we've done that for few, but not for all of them. We've done that sort of careful tuning. We just sort of done an optimization. But the idea is that there's so many lines that maybe the details of that energy level structure don't matter too much. It's just sort of just how many lines are there rather than the details of what the energy level structure is. So you might think that the heavier elements, they have more electrons, they must be more complex, have more levels and lines. That's not quite right. What really matters in complexity is where you lie on the periodic table. And so this is basic atomic physics that if you take elements, say, in this column here, which have valence electrons in the S shell, they're relatively simple elements, and there's only two ways to put an electron in the S shell, spin up, spin down. There's not a lot of configurations or levels or lines for these elements. These guys, which are an L equals 1 valence electron shell, are a little bit more complex. You have 6 states you can figure electrons in a variety of different ways that will sort of all eventually be broken through interaction effects or something. So you get sort of more levels here. The D shell electrons are somewhat more complex. So here sits iron, it's one of the more complex elements. We have ordinary astrophysical mixtures. What's really unusual here in the neutron-star merger ejectas, you also produce these heavy elements in the lanthanide series, and even up into the actinide series that are S shell, and they're way more complex. They have a lot more levels. And you can actually estimate that with a simple kind of combinatorics to say what are the number of ways of putting n electrons in G valence electron spots, and then the number of lines will be sort of the square, different levels. So if you just do this estimate, you'll see that these elements sort of have 100 times or more lines than typical astrophysical stuff. So we expect, just on basic atomic physics grounds, that the number of lines against the opacity of these heavy lanthanides and actinides will be 100 times or more greater than typical iron group elements. That's kind of shown here. Here's energy level structures that are calculated or just known. So here's your well-known hydrogen, and test shell. Here's silicon, it's a little bit more complex since it's peach shell. This blue region here is showing you sort of the region that can be thermally excited and populated in these kilonova. Here's iron, D shell, a little bit more complicated. And here's a lanthanide. And the energy level structure is incredibly dense. There's just so many different levels, so many different transitions. You can imagine being a photon trying to move through the neodymium. Almost every wavelength that you're at, there's some transition that you can hit. And so the actual atomic structure calculation we've done here kind of agrees with the simple analytic estimate of how more complex the neodymium should be. This translates directly into it. And so here's an actual calculation of opacity as a function of wavelength for some of these elements. These are, again, they're just a bunch of lines that all blend together into a pseudo-continuum, which gives it this jaggedy shape. But you can see iron compared to, say, a lanthanide like neodymium is down that factor of 100 or so. Where something like osmium, which is a heavy element as well, is similar to iron, because osmium is basically a lot of iron. So it's very similar opacities. This just goes to what I said. We don't know all the details of all these lines exactly, but there's so many of them that they all sort of blend together statistically, and so even though their details can be different, sort of on average, capture the right general behavior. So there's uncertainty still in those opacities, but we've sort of rounded it with some basic atomic physics. So here's the effect of high opacities on some of these kilonova light curves before they sort of peaked in a day or so. With higher opacities, of course, the diffusion time becomes longer, so the light curve peaks after about a week or so. And it's a little bit dimmer because it's kind of spread out that energy over time. And then the more dramatic effect is that the strong opacities of these lanthanides sort of blanket the optical region and push the photosphere out to cooler temperatures. So instead of getting this nice optical kilonova now, you're seeing emission at basically peaks, sort of in the micron to micron range, with very little emissions from the wavelengths. And so, I guess on the one hand, this is depressing for people trying to look for these kilonova and optical wavelengths. On the other hand, it provides a really effective way to try to discriminate these events from other sorts of transients. Other sorts of supernovae tend to look more like this in the optical. So if you could get, say, a B minus, a high color or something, it would be quite a distinctive signature of seeing the kilonova and sort of picking out which object you want to spend your time following up. There hasn't been much follow-up of gamma-ray burst sources, supposed neutron star mergers in the infrared. And one sort of example that we followed deep was this GRB in 2013, where they followed it up a week later. And it didn't see much emission in the optical, but it did see some bright emission in the infrared. It's hard to say what this is. It's just some, one data point of glow, which then faded away. Could be something to do with the weirdness of the afterglow. But if you try to compare it to a kilonova, the main thing is you have one data point here, but you can try to say something about the mass, if it is a kilonova, the mass of the material that was ejected in the kilonova. So this is a light curve calculation for a 3D model that looks like this. This is one of Roswell's simulations. So it's actually Newtonian simulation, which looks a little different than the GR ones. But here's the optical light curve, which again is pretty dim because of this high opacity blanketing. Infrared is much brighter, but it depends upon your viewing angle. So for this donut shape, the kilonova is brightest if you're looking sort of face on to the donut. So you have a bigger projected surface area that you can catch on. So it's sort of a factor of 3 variation in brightness for the particular. And so for that HSD data point, if that was a kilonova, we know the viewing angle because we were looking at we saw the GRP sort of looking down the pipe. And you can sort of compare it to one of these data, one of these models, and actually constrain the amount of mass that you would need to actually explain that thing. And it turns out to be something like 0.025 solar masses. Now, there's a lot of uncertainty there because this is just one data point, and there's uncertainties in the model, both in the opacities and the structure of the projector. But it's a proof of principle of what you could do if you had good data and good models. You could fit these data with light curves can actually infer the mass of our process material. And this is a pretty large number. It's at the higher end of what we'd expect from these things based on simulations. And so if the rate of neutron star mergers is something sort of the middle range that people think, and they all eject this sort of mass at each time, then you actually can explain all of the R process elements of the universe through neutron star mergers. This is a starting point, but you can imagine getting further on as we get better data from LIGO on the rates of these things. If we had many kilonovae, you can actually constrain both of those things pretty well, add up the R process from neutron star mergers.
So, yeah, I mean, this is pretty interesting. So can I push you a little about this? So what jumps out at me is that number has two sig figs with it.
Oh, yeah.
0.025. And so I'm curious, are there not other model parameters that could slosh around here and move that number up or down? What if this neutron fraction is higher or lower, for example?
Yeah, that's a good point. I shouldn't put two sig figures. I put a little here. So it's not very accurate to the factor of 2 or something, probably more, because again, there's uncertainty about the composition and the opacity. And there's basic uncertainty in atomic physics at some level that cause that problem. And then the opacity, the composition of this material, the geometry of this material, its velocity. We can't constrain very much. If you get a lot of data, you can start to break some of those geometries. Let's say how fast it's moving versus how much material there is, or how much is coming out in blue versus red. So yeah, this is not a very accurate number, other than to say it seems like the mass you need is pretty on the high end. But it sort of points to what you might be able to do in the future with better data and better models. Okay, so let me turn to some more recent work trying to understand this other component of the kilonovae that may be there, not the material that get flung out in the merger itself, but these winds that came off the disk afterwards. And what we found there is that you may be able to have conditions where you get optical emission, not just infrared, which is helpful for people that are trying to look through these things in surveys. And so here's the basic idea I mentioned before. After the merger, you have some compact object, maybe a black hole with a disk around it, and it'll feed on some viscous timescale. So these are hydrodynamic simulations done by Rodrigo Fernandez. These are basically just 2D hydro simulations with an alpha viscosity to mop up the viscosity. Really, you'd like to do this in 3D with NHD to really capture the viscosity, but this gives a good picture of what's going on. Here's the density, and here's the YE, which starts out pretty low because it's neutron star material, but it will evolve due to weak interactions that happen in this disk over this time period. For example, there's strong neutrino irradiation of this disk, and neutrinos can flip neutrons to protons and vice versa. Absorbing a neutrino or anti-neutrino or other processes as well. And so, since the emission here tends to be kind of nearly equal amounts of neutrino and anti-neutrino luminosity, the neutrino irradiation tends to drive into a more symmetric neutron-to-proton ratio, actually YE closer to 0.5. So since this material sits in this disk and creeps for a while into this radiation, you see a somewhat higher YE in the material of the disk and the stuff that gets blown out. Here's reaching YEs at 0.2, maybe a little bit more in the simulation. And if you have a higher YE, you may actually lead to quite a different composition at the end of the day, which will affect what we see in the kilonovae. So here's another one of Jonas's calculations with a higher YE. This is 0.25. Again, starting out with some C's. And you'll see as we let this evolve, the neutron captures occur, and this thing starts to move up the charged nuclei. But it basically gets hung up at this closed shell. Since the waiting time for data decay is pretty long there, there's just not enough neutrons to get you past that shell. And your composition sort of dies out before you get to the heavier elements. And so you actually, for these higher YEs, reaction networks that I ran with different code showing the abundance is a function of atomic number. For the lower YEs, you build up, as I showed before, these sort of almost all strong R process elements that go up and include these lanthanides. But as you go to YEs a little bit higher, say 0.3 or 0.4, the nucleosynthesis flow gets caught up at that closed shell nucleus, and you never get heavy enough to produce the nucleons. So for higher YE, you get a very different signature than Kilonovae. You won't get those high capacity materials as you do for the lower. So it becomes a very important question: what is the YE of these outflows? What's the composition? And simulations that Rodrigo has done again for a black hole source. You get YEs that may reach about 2 or something. If the remnant stays for some period of time as a hypermassive neutron star, you get a lot more neutrino radiation. So neutrinos radiating a huge amount of neutron stars, radiating a huge amount of neutrinos. You can see the neutrino thing here. And as I said, those neutrinos tend to raise your electron fraction to something more closer to 0.5. So you can get higher YEs here, 0.3, 0.4. Now, these calculations assume a pretty simple treatment of neutrino transport. It's just sort of a new scheme. But it's capturing the main effects. Another thing that may be happening here is the black hole spin can have an effect if you have a spinning black hole, which is probably the more likely outcome of the merger. Then you move the sort of inner part of the disk even closer to the black hole. It's in a more stable orbit, and you have a sort of higher potential. You have a hotter region of the inner disk, and you have more neutrino radiation. It's comparing it to a non-spinning black hole to one with the curve parameter at 0.8. And you can see this is a YE here. For the 0.8, you have more neutrino radiation, and you get regions of higher YE above sort of 0.25 level, 0.3 or so. So you may get some free material here. All that assumes some sort of simplistic neutrino transport. We've been working, CaJAGWR has been working and trying to improve that and doing some real Boltzmann neutrino transport through Monte Carlo techniques coupled to this new neutrino library developed here in Caltech. And here's some initial results showing sort of comparing actual full neutrino transport to kind of leakage schemes that people often use in neutrino codes, showing some qualitative similarity for a hypermassive neutron star. Some differences here for a black hole remnant where you get sort of more neutrino heat radiation above the disk in that case. So this is sort of work in progress to try to improve our simulations and get a better idea of what the YE of these outflows would be based on the neutrino transport. But the basic picture that seems to be emerging is that the ejecta from these winds probably looks qualitatively something like this. It's roughly spherical, so these winds are they're not completely spherical, but they're mostly spherical outflow. Some axis ratio of 2 to 1 or something. And the outer regions tend to be more subject to that high neutrino radiation and have higher YE here. So we might have YEs of 0.3, 0.4 in the outer region. The inner region may have had less neutrino radiation, perhaps because the neutron star collapsed to a black hole at some point. Turned off. So you may have sort of a low YE core surrounded by this high level spin. And so here's results of a survey study we did with these simulations to try to see what's the composition of the material ejected in these winds, depending upon the lifetime of the neutron star that forms at the center. And that's something, again, we don't know very well. It depends on those details I said, the equation of state, matter and stuff. That requires a separate simulation to really calculate the collapse of the neutron star with a black hole. But just taking it as a parameter and considering cases where the neutron star collapses immediately a black hole to the extreme case where the neutron star survives forever. It's just showing you how much mass gets ejected in winds at different YEs. So for prompt black hole, you get fairly low YEs of less than 0.2. As you leave the neutron star longer, you get higher radiation and your YE moves up, and eventually you can go into this region above YE 0.25, where, because again, the nuclear physics, you don't make the heavy elements, you don't make the main mass. And you also see you get more mass ejected as you go to longer neutron star lifetime. Simple reason for that is just that the neutron star has a hard boundary, so stuff can't fall into it. It just builds up on the given that your neutron star never collapses to a black hole, you wind up eventually ejecting all the disk in the wind, because there's no black hole to suck up the material. So that's the qualitative picture we have from winds, and these are the kind of predicted kilonova lag curves we get based on those models, again, different neutron star lifetimes. And so for a prompt black hole formation, you know, you'll get a little bit of low mass material giving a little bit of optical emission. But again, most of the kilonova is coming out in the infrared because you're making mostly very heavy elements that have these lambda-9 capacities. But as you go to higher neutron star lifetimes, then more material comes out of this lambda-9 free wind. You start getting more and more optical, and the limit that you have a very long-lived neutron star, actually most of the emission will turn out to be optical. So you sort of destroy those high opacities by neutrino radiation. And so this is interesting. For one point, it may mean that the optical observers have a chance of finding these things with optical surveys because there may be a component that's blue. And it also means that if you measure both the optical and infrared component, having some handle on some of the interesting physics that's going on. For example, the lifetime of the neutron star. You distinguish these two cases in observations. You can tie it back to some of the physics that's going on, like how long the neutron star lasted before it collapsed. So kilonova is giving you a more detailed picture, at least some insight into what's going on in physics. One interesting aside that came out of that is that you can predict these optical blue light curves for some models with different parameters of neutron star lifetime. And interestingly, there was a GRB that went off about 5 or 6 years ago now, where they did see a little bit of an optical transient following the short GRB. And it came early, and they didn't make a really big deal of it at the time, mostly because they didn't know the redshift of this object, so it was hard to say how bright this emission was. But if we take a sort of reasonable value of that, just pick a value of redshift of 125, you see that this transient that was observed in this GRB kind of matches pretty well with one of these disk wind outflows for a neutron star merger that we have. So nothing conclusive here, but just showing that this may be an example of something that could be connected to kilonova emission from these highlight disciplines. So now the picture of kilonova is getting more and more sophisticated. Initially we said we had this dynamical material, maybe it's a tidal tail being flung out. Then later this disk wind comes on, it's moving a little slower, so it's expanding out into this tidal tail. And so we have this sort of multi-component picture of what a kilonova is. It's not a monolithic thing anymore. And a more schematic view might look more like this. Again, we had in the center, we had wind, it's moving a little bit more slowly. The inner regions may be low IE, so maybe high opacity red emission, but maybe covered with this skin of higher IE irradiated material. And we may have dynamical ejecta sitting around there. And actually the very surfaces of these dynamical ejecta that's moving very fast actually can have some component of free neutrons in there. And you may see some emission from free neutron decay power. Brian Metzger has discussed. It's just sort of a brief UV emission. So you have this now multi-component picture now. And they have kilonova radiating in different ways. Each thing telling us a little bit different about the physics. One thing you worry about this is that if I have these disk winds that may have some blue emissions because they have low opacity, they may be embedded in this high opacity dynamical ejecta. And if that's the case, you may be completely excluded from seeing blue emission at all. Sort of lambda-9 curtain around you. And if that's the case, it may be hard to see the emission, but it will depend upon viewing angle. So you can imagine this picture. If you were looking at this kilonova from this viewing angle, it'd be really hard to see through this tidal tail, which is very high opacity material. But if you're looking, say, straight down on it from other angles, you may be able to see in to this disk wind that's producing optical emission. And that's kind of what this schematic calculation is showing for a 3D model. The blue here is showing the disk wind. The red is a tidal tail ejection, mergers, and you can see if it had this geometry of sort of toroidal dynamical ejecta, then when you're looking face on, you start to see the blue emission coming out from the lens. When you start looking edge on, that high opacity from the dynamical ejecta starts to block your view. You just see infrared, you suppress the blue. So whether you can see optical emission or not may depend also upon the viewing angle in the geometry of this ejector. Here's some spectra of the events just to show you what kind of information we may get. In the future, we could actually use a telescope. We may need something like TMT or something to get a spectra of some of these two things. But there's a lot of information as well in the spectra if you take it. The challenge is this plant-rich material where you have to take an infrared spectrum. The main thing to notice here is that the dynamical ejecta of these starters, as I said, is moving quite quickly, as you see. So the spectra, again, have very broad features that tend to get washed out. So you see some sort of undulation here due to the features that go clear, sharp features. And so seeing something like that, taking a spectrum of something like that, would be sort of a smoking gun that you see in Kilonovae. It would both be indication that infrared would be some indication that you had these heavy elements around, and the broadness of these features would be indications of the high velocities. It's hard to think of anything else in the universe that would give you that sort of event. And then the wind, I said, is moving much slower, several times slower. And so it's slow enough that you can actually start to see individual line features. And again, we're not very sure about the position of all these line features because the atomic data is not really good enough to predict the wavelengths. But that's something that will get better over time as we build better atomic structure models. We can calibrate it more to experimental data. At least you can imagine sometime in the future, if you had this data, you can try to start identifying line features and connecting it to a sort of more detailed picture of the composition of these kilonovae. Which would be an amazing thing in terms of diagnosing the sites of the art process. I mean, right now we don't even know where the art process is made. If we could find these things, it's a chance to look directly at sort of pure art process material, in its site of production, and actually do spectroscopy of it and try to pull out direct information. It's going to be very hard, both observationally, to get through this data, and in the modeling sense, to get good enough input data in models to predict these spectra. But in the future, some direct probe to try to understand more about our processing systems. So just to put it all together, I'm going to talk about this color, this kilonova, and it's kind of nice how the physics puts you in sort of two different channels. The color that you observe is a really strong diagnostic of the physics that's going on, right? So talking about this, if you have some low YA ejecta, some dynamical ejecta, you produce lanthanides, that gives you a high opacity red or infrared kilonova. If you have high YE, you have no lanthanides produced, lower opacity, you get some illumination. And what's really nice about this, although it's all kind of theoretical and based upon modeling, is that there's basic physics that kind of underpins each piece of this. So I said before, there's this nuclear physics fact that there's this closed shell, that if you're too high a YE, you don't have enough neutrons, you get stuck in that shell, so you don't produce these lanthanides. It's kind of a nice coincidence that closed shell happens right before you start producing lanthanides. So there's a nuclear physics reason why you break up into these two branches. And then there's a nice little atomic physics reason why the opacities depend so sensitively on whether you have lanthanides or not. And that's just the argument I gave you of the orbital valence electron shell where you have an F shell, valence shell, or not. And so although there's a lot of approximations and uncertainties that goes into these models, we can take a bit of confidence that at least they're grounded in some pretty basic things that we can trust. And again, what puts you on these two channels may be something about neutrino radiation. If you have high neutrino radiation, you tend to drive yourself to a higher value. That might happen in disk winds, get lower than the And so kind of the picture is a dynamical ejector or disk winds without much of radiation, say from a non-spinning black hole. You get disk winds with a longer neutron star. They get high radiation, there's a high spin. We put you there. So the idea is information about just sort of drawn a picture and sort of paved the way of the trends that we want to see. There's a lot more that needs to be done to really make these robust theoretical predictions. Again, the disk winds we've done have just been 2D alpha disks. You really want to do that with 3D MHD, and there's efforts underway to do that. You want to do the neutrino transport better, since that's crucial for setting the YE of the objective. So I'm sure was working in that direction. You want to do better nucleosynthesis, which was Jones and other people trying to build better nucleosynthesis post-processing into different compositions. You want to understand the radioactivity better, how it thermalizes, and again, the radiative transfer to improve our opacities and all these things. But there's a step forward to sort of make progress on all these fronts in the next few years, so we can build a more robust theory. And I guess, yeah, just some of the key takeaways these I've mentioned already. Yeah, you still know we could direct probe to our process synthesis. And we could use that actually to address this question of where the R process elements came from. If you combine LIGO rates of mergers compared to Kilonovae light curves over the measure of the objective mass, you multiply those two numbers and you basically weight out the amount of R processing numbers. You can ask, is that enough to explain what we see? The color is a strong diagnostic of what we're having, and we make that example. So here's just a little cheat sheet we put together to try to map different neutron, different compact object binaries to roughly where they may appear in terms of neutron star. You may have a few different cases. You may have a hypermassive neutron star going to a black hole, which could be some infrared and some blue emission. If it goes promptly to a black hole, you may not get as much blue emission as the red neutron star black hole. Depending on its spin, maybe some kind of red emission. And so, yeah, I look forward to the future where we have LIGO and astronomical surveys following up to try to take this theory and bring it into the world of real data and interfacing these ideas with reality. So thank you very much.
Time for a couple of quick questions.
Can you say a little bit more about the neutron star and black hole case? I mean, presumably it depends a bit on the mass of the spin of the black hole that you converge in, whether you get it is as opposed to this type of ejection. I guess it's like consider anything that a fight of Mars or when you get a disk wind in that case.
Yeah, you can build up
You
tidal disrupt. Yeah, you can build up a massive disk around a black hole in the neutron star black hole case. And it is somewhat sensitive to an asteroid. You can actually build up larger disk masses in that case than in the neutron star case. But that one GRB where they had one data point of, it was an exceptionally bright GRB. Some people speculated that maybe it was a neutron star black hole merger where you built up a bigger disk mass and part of brighter GRB, and you had more material around to eject Kilonovae, which may explain why you need such high ejected mass.
But there could be two cases of the blue and the red case for those as well, depending on the mass ratio.
Yeah, right. Yeah, I mean, the disk wind from the black hole could be, it could be either low YE red emission, it could be higher YE emission, depending on, again, this is a little uncertain, but it depends, on the spin of the black hole somewhat. So, yeah, so there could be two cases. It's sort of, what this is suggesting here is that as you increase the spin of the black hole, you're sort of increasing your blue component relative to the red.
Any more questions?
When the Christus people started putting MHD into the MHD into their calculations, simulations,
MHD, it's the informative jets, we just looked at the land. Yeah, you're right, there's another component to all this story, which I didn't talk about, which is you blow off the material on the wind or in the tidal wind. But then you probably launch a jet, a GRV jet, and it punctures through. And that would presumably change the geometry of this Kilonovae debris. It would push aside material and pull and change it, and change its geometry. And something that hasn't been included here, but it's another component that will sort of add a little bit of complexity.
The field might even change the geometry of the wind itself to level and produce a jet as well, so.
Yeah, so yeah, you have to take with a grain of salt the sort of alpha disk winds that we see, because, and also the composition as well, because yeah, 3D MHD you may have different dynamics. You may have a shorter resonance time in material and disk before